All right, let's start. Electric electric power. Again, today is going to be we're going to be talking about solely electric power. So, for electric power, I want to talk about how that relates to the regular power we've learned thus far, right? So far we've learned that power is work over time. So, rate of energy done per unit time. Now, electric power is very similar, mainly because it's the exact same formula. Well, electric power has more to do with circuits, right? And you see these circuit boards on this image right now. So the green one on the top left is something that we are gonna well, if we ever return to the lab, return to school, we will use these circuit boards. These are circuit boards that the school ordered this year. Well, I made them order this year. I didn't make them. I asked Mr. Walsh to order them this year. All right, and he agreed. So we have 16 of these, and we have light bulbs. So the light bulbs fit here on the yellow circles right here. You'll see them say lamp. But for the most part, we're probably not gonna use it. Probably because we might not even come back to school, from what it looks like. So if you take a look on the right hand GIF, you'll see that he's generating electricity somehow by moving this thing in a circle. We'll talk about more ways electricity is generated in the real world later, because this is usually how things are generated in the real world. But more at a more larger industrial size. So again, we'll talk more about how electricity is generated later. But for now, we I just want to focus on this on electric power. So again, uh, he- something's happening here. So electrons are moving from through this circuit, through this wire, and it's powering this object at the end. All right. So again, the electricity are electrons. Electricity is the flow of electrons. And for electricity to flow, there needs to be wires connecting. So outside, you do see all those wires on the poles up. So that's how you get electricity. And obviously, there isn't a spark being generated outside. Uh, and again, it's an exaggeration, right? It's showing you that electricity is flowing. Now, I want to talk about electric power. Electric power is the rate at which electrical energy is transferred through the circuit, through the entire circuit. How much energy flows through the circuit at any over time? How much yeah, how much electrical energy can flow through a circuit through a given amount of time? It's different from electric current because electric current is the amount of charge per unit area. So you're only taking, for example, yeah, you it's only per unit area, right? You're not per unit area over time. Whereas electric power is the rate at which electrical energy can flow through in the entire circuit, right? Electrical power is the rate at which energy can flow through the entire circuit, and is the rate at which work is done to convert the energy into another type of form is called electric power. All right. Now, appliances in the real world, they're rated using kilowatt hours. You guys will probably only see units in high school regions, watts, right? Watts seconds. But appliances, electronics in the real world, they're measured in kilowatt hours, right? So now let's move on to solving problems because that's what we're here for. On your reference table, these are the formulas you should see. All right, so all the formulas are on the fourth page of your reference table, and they're all the way over here, right? Right here, right here. These are the formulas you're going to use. All these formulas right here, and it might look like a lot. It might look like a lot, but trust me, it's not. It's not. It's not. Trust me. All right, so let's do electric power. The worksheets now. So, number one, to increase the brightness of a desk lamp, a student replaces a 50-watt incandescent light bulb with a 100-watt incandescent light bulb. So your power is 50 watts, all right? And your other the other light bulb is 100 watts. So in compared to the 50-watt light bulb, the 100-watt light bulb has less or more watt. So they want to they're talking about resistance and current. Okay, they're talking about resistance and current. That's what we care about right now. And we want to know, well, what happens to R and I if power increases? Now, this is one of the harder questions in this problem because there's an assumption that you must make. The assumption that you must make is that even though you're changing the wattage of these light bulbs, your voltage remains the same because you're still plugging it into an outlet, and the outlet will always give you the same voltage. So your voltage will always remain the same. So, so let's take a look at this formula right here. P is equal to V times I. Well, if you increase your power and your voltage stays the same, right? If V stays the same, then I must increase. So we know that if power increases, then I must increase as well. Because again, if we do 50 is equal to 1 times 50. Well, if we increase the power to 100, well, the 1 also, your current must also increase. So your current must increase. Now, let's take a look at power is I squared over R. Okay, power is I squared over R. So if you increase your power, actually, hold on, this is the wrong formula. Let's take a look at this other formula. V squared over R. If you increase your power on this side, and if voltage stays the same, what must happen to the bottom? Right? Let's take a look at this. Well, if you don't want to think about it conceptually, 1 is equal to 1 over 1, right? And so those are the numbers. So again, 1 squared is 1. Well, if we increase here, so 2 squared, remember 4, okay? So let's say power is 1, voltage is 2, and R is 4. But if you increase your power and you go from 1 to 2, so let's say this 2 now, your voltage stays the same. So what does your R have to be to get 2, right? Because if you have 4 on the top here, what number do you want to have down here for your power to be 2? Well, your R has to be 2, right? 4 divided by 2 is 2. So when your power increased, your resistance decreased, okay? So when your power increased, your resistance decreased. So if power increases, current increases, and your resistance decreases. Now, the reason why we can't uh, use P is equal to I squared R is because we can't tell whether or not one thing is changing. If we know that, well, if I squared goes up, if I goes up, and well, R must come down. We don't know what's happening here. We need to separate it into the individual variables, right? We have to know whether or not something is constant. We need to have a constant variable that we know is constant before we can make a relationship. All of these numbers are in flux besides power. We know power is going up, but we don't know what's happening to current and resistance. We need a constant. We need a reference. And so that's why I use those formulas. So number 2, a 3.6 volt battery, right? 3.6 volt battery is used to operate a cell phone for 5 minutes. So time is 5 minutes, and if we were to convert minutes into seconds, 5 minutes is 300 seconds. If the cell phone dissipates a power 0.064 watts of power, the current that passes through the phone is what? So now what you're going to do is you're going to look through all these variables, okay? You're going to look through all these variables here, and you're going to match which one has everything. So let's look at the top. Power, we have V power I. So we don't even need time here. We see a formula right here. Power is V times I, right? Power is V times I. So power is 0.064 watts, okay? Your volts is 3.6, and you want to find out what I is. So now you're going to divide this number by 3.6, and you're going to get probably 0.018 amperes. Yeah, most likely. Most likely. For this four, yeah, pretty much. So the answer is A. Answer is A. So again, all you're doing here is you're seeing which knowns you have, and then you're plugging into a formula. That's awkward. Anyway, 3. A light bulb with a resistance of 2.9 ohms. So your resistance is 2.9 ohms is operated using a 1.5 volt battery. So your voltage is 1.5 volts. At what rate is electrical energy transformed in the light bulb? Again, electrical energy is your work. So now you're going to look at your formulas. Right, you're looking at your formulas here. Well, which one has everything we need? 0.5 volts, work done, resistance, work is power times time, power. So this is a two-step problem. So first, okay. It says what is the rate at which electrical energy is transformed? So the rate at which electrical energy is transformed is power, right? That's the rate at which electrical energy is transformed. Electrical energy itself is work. So that's electrical energy. But rate at which electrical energy is transformed is power. Rate at which energy is transformed. So we want power here. We want power. So power is equal to, that contains V and R and P. The only formula that contains all your knowns is this. So 1.5 squared, 2.9. You're most likely gonna get a decimal. That's for sure. It's probably B. But let's make sure. Yeah, it's B. So you get 0.78 watts, and that's your answer. 4. An electrical circuit contains a variable resistor connected to a source of constant voltage. As the resistance of the variable resistor is increased, the power dissipated in the circuit does what? So your resistance, so it tells you your resistance is changing. Your voltage is constant, and your resistance is increasing. And the power, and they want to figure out, well, what happens to your power if all this happens, right? So what happens to power? And so in the last problem, you'll remember that power is v squared over r. So if your velocity stays the same, and your r increases, what happens to power? Well, yesterday we also know that if you increase something on the denominator, you're decreasing something on the other side. All right. If you don't want to use, if you don't believe me, you can use numbers, and I'll let you use numbers yourselves. Okay. I'll let you use numbers yourselves. Actually, since I want you to prove it, I want you to prove it somehow. So let's do. Actually, I proved it last. Yeah, I proved it already. So the power dissipated decreases. Okay, so it's A. It's A. It's A. 5. Amount of electrical energy consumed. So now they actually want the amount of electrical energy. So they want your work. Consumed by a 60-watt light bulb. 60 watts for 1 minute. So 1 minute is 60 seconds. For 1 minute, could lift a 10 Newton object. So your weight is 10 newtons. Your force through gravity is 10 newtons to a maximum vertical height of what? Well, this is the amount of energy consumed by to a maximum vertical height of okay. So you have to apply a few logic to this. So power is work over time. All right, so power is work over time. So 60 watts, work, 60 seconds. So 60 times 60, because you want this on the other side. So you get 3,600 uh, joules of energy. So that's your joules work. And now that you have your work, you know your work is your change in total energy. All right, it's also your force times distance on your reference table. So what we can do right now is 3,600. Your force due to gravity, well, this is basically potential energy because potential energy is Fg times h, which is basically Fd. So this is force, 10 newtons, distance, solve for distance, and you get 360 meters. And so the answer is C. If you made it this far and you don't understand what went on, that's fine. Skip this question because it's not. Yeah, you can skip this question, but you should still be able to do it. It's not that hard. You're just applying concepts from two different units because all these things are related to each other. I'm teaching you them all separately, but they all relate to each other. So number 6, a hair dryer with a resistance of 9.6 ohms operates at 120 volts for 2.5 minutes. So 2.5 minutes is 150 seconds. The electrical energy used by this dryer during this time interval is what? So this time you actually want your work. So we take a look at our formulas again. Well, which formula has everything we have here? Well, work is V squared over T divided by R. Okay. So work is 120 squared times 150 over R, which is 9.6. So 120 times 120 times 150, and you divide that by 9.6, you get 225 that, and this comes out to, since there are 5 decimal places, right? There are 5 decimal places, so 2.3 times 10 to the 5 joules, and so the answer is D. All right, so 7. A particle with a charge of 3 elementary charges, right? So you have 3 elementary charges, and you move through a potential difference of 4.5 volts. So that's your voltage, that's your potential difference. What is the change in electrical potential energy of this particle? So you want your work done, right? What is the work done on this particle? Now, this is a very difficult question. You have to make a lot of you have to make a lot of connections here. Right, okay? So let me walk you through. Well, let's let's first convert this charge well, let's convert this elementary charge into an actual charge. Okay, so we know that one elementary charge has, well, 1.6, right? 1.6 times 10 to the negative 19 coulombs. And so 3 of these is going to give you a charge of 3 times 1.6 is 4.8. So your total charge here is 4.8 times 10 to the negative 19 coulombs. But if you take a look at your formulas, you don't really see Q here, right? You only see V and you see W, but you don't really see Q. But the thing is, you also know in the first lesson, I is delta Q over T. And if you move T to the other side, what you're going to get is IT is equal to delta Q. Well, guess what? Look at the formula for work on the bottom. Work is equal to V times I times T. Right? So work is equal to V times current times T. Well, if current times T is your charge, this becomes delta Q, V times delta Q. And now we can solve. So 4.5 volts times 4.8 times 10 to the negative 19 coulombs. You should get, I think you get B? No, I can't do that yet, though. I'm sorry, don't, just ignore me. So let's do 4.5 times 4.8. So you get 21.6 times 10 to the negative 19 joules. So again, this is measured, work is measured in joules. But the problem wants the units in electron volts. So let's actually erase all of this first. And so again, we have our work. Our work is 21.6 times 10 to the negative 19 joules. On your reference table, and I'll show you, let me just bring it up. On your reference table, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. All right, so if I were to convert this work into electron volts, what I would have to do, how many electron volts are in this amount of work? So 1.6 times 10 to the negative 19 joules divided by 1.6, 10 to the negative 19. And you should get, you should get like 10? No, not 10. 15? No, not 15. 13.5. Yep. 13.5 electron volts. And so that's your answer. I mean, it's one of two choices. Which choice makes the most sense, right? Because it's not going to be C. 1.5 times 1.6 is not 21.6. But 13.5, that sounds like a realistic answer. So now let's do 8. Let us do 8. Which object will have the greatest change in electrical energy? Electron moved through a potential difference of 2 volts, so that's choice A. Metal sphere with a charge moved through a potential difference of 2 volts. So they give you the charge now. Well, the charge of one electron is negative 1.6 times 10 to the negative 19 coulombs. Voltage is still 2 volts. Q is now 1.0 times 10 to the negative 9 coulombs. C is the same thing. Voltage is 4 volts. Q is negative 1.6 times 10 to the negative 19 coulombs. And D is same thing, 4 volts. Okay, so we go back to the same formula we used last problem, where we do work is equal to VIT, and we know that IT is equal to delta Q. Why? Because I is equal to delta Q over T. We're moving T to the other side, so that's how we get Q by itself. So we know that V, since IT is equal to delta Q, we know IT right here. We're just going to substitute IT with delta Q. So which combination of numbers gives you the highest work? Well, because it's very straightforward. It's like a multiplication thing. You just pick the highest numbers. Okay, the highest numbers give you the most work. 10 to the negative 9 is larger than 10 to the negative 19. So it's either going to be B or D. And 4 volts is greater than 2 volts, so it's most definitely D. D gives you the greatest numbers. All right, D gives you the greatest numbers. So the answer is D. All right.